Welcome back to our discussion on surface chemistry. We are continuing from where we left off last time, and this is the second session in this discussion on surface chemistry. So, we will first, before we start new things, we will recapitulate what we did in the last discussion. We first talked about what this chapter contains, surface chemistry, and that it contains discussion on surfaces, catalysis, and colloids, and how these three apparently disconnected topics are all related to surface phenomena. And then we also discussed how, as you decrease the size of particles, the surface area increases. We took the case of a cube and then kept subdividing it into smaller and smaller cubes, and then we showed that as the size decreases, the surface area increases. So, as the particle size goes down to from macroscopic to where we are looking at heterogeneous catalysts or colloids, we are going to see very important phenomena happening on surfaces. We also illustrated percentage of surface molecules and how that increases as surface area decreases. The particle size decreases. So, that is pretty much what we discussed last class, and we were talking about, we started our discussion at the end of last class on the differences between adsorption and absorption. So, when we have any material, and we are in all our discussions thus far, we are looking at primarily the solid gas interface. If you take a solid, any solid, which I have just represented as spheres in appropriate locations, any time I have a surface, I will have both adsorption, which is a surface phenomenon, where a particle which is in the phase above it gets attached to the surface. So, this would be an adsorbed molecule, whereas if the particle went and sat inside the solid, this would correspond to an absorbed species. And what we are going to try and look at is primarily the adsorption. We are not saying that absorption does not happen at the same time. We are just saying that because the surface area is so large, the adsorption phenomenon is going to predominate, and that is what we are going to look at with gas adsorption, let us say, on solid surfaces. So, let us think of the experiment that we are doing. We have a solid in this case made up of spheres, and like any solid, they sit in fixed positions. The atoms or molecules that make up the solid sit in fixed positions, which is what the solid state of matter, the situation that we have there. And on top of this surface or the solid, we have some gas or liquid, which I have represented here by red dots. And let us imagine the situation where this whole thing sits in a container at a particular temperature T. So, I have some mass of solid the one which has this surface here, and some amount of gas, also a known amount of gas mass, let us imagine, on top of the solid, and it is in an enclosed container. And let us imagine that I attach to this a gauge which measures the pressure of the gas on top of the solid surface. And what we have already said from preliminary discussion is that when you have molecules of the gas on top of a surface like this, some amount of the molecules from the gas phase will get adsorbed on the solid surface. So, if I have a larger surface area, then I will have more gas in the gas phase get adsorbed onto the solid surface. And what we are going to now try and do is to look at how much mass of the gas that is on top of the surface get adsorbed onto the surface per unit mass of the solid that we have. That is the experiment that we do. So, what we do is you take, let us take the solid, you heat it up such that everything which is there in the solid goes away. So, there is any adsorbed species, any absorbed species, etc. You evacuate it. So, you heat it first. So, the things which are there which are adsorbed already in the solid goes off. You put a vacuum on top of the solid to ensure now that you have a pure solid. You put it into this container that we have, add some gas on top, put a pressure gauge there, and then after equilibrium has established, you measure the pressure. And since the pressure is related to the number of moles of the gas at a particular volume and temperature, we can determine how much mass you put in initially, and after equilibrium is established, we know the pressure, and since we know the volume, we know how much gas is left, from which I can determine how much of mass of gas got adsorbed. And if I know the mass of the surface, that is the solid that I put in there, I then evaluate this quantity, which is x over m, which is the ratio of mass of gas adsorbed over the mass of solid. So, that is per unit mass of the solid that I have got, I am trying to measure how much gas is adsorbed. This is the experiment that we do, and we are just measuring the pressure here. Okay? And this is an experiment that Herbert Freundlich did, and here is the data that Freundlich obtained. This was somewhere in the 1900s, and we are looking at the adsorption of argon on coconut charcoal. That is, you take coconut husk, you burn it and you get charcoal, and then you take an appropriate amount of this at minus 78.3 degrees Celsius is where Herbert Freundlich did this measurement. And here is the table of the pressure expressed in centimeters of mercury, which is some unit of pressure, and what he measures as A, which is this ratio x over m. And this is the table that Herbert Freundlich reported in 1910. So, at 0.8 centimeters of mercury, which is the pressure of argon on top of the solid, he measures the quantity A to be 1.6. Note that this is unitless because this is the ratio of the mass of gas adsorbed over per unit mass of the catalyst, in this case coconut charcoal. When you have 1.9 centimeters of mercury, he says A is 3.7. At 2.4, you have 5.0. At 5.42 centimeters of mercury, he measures coverage to be 9.9, and at 9.84, it is 15.4, 12.9, it is 18.6. And his table goes on. Because I have run out of space, I will stop here. But this is, I am writing this to give you an illustration of the kind of measurement that he has made. What you do is, you adjust the pressure on top of the solid, and in one case he takes 0.8, and then he looks at what happens to the gas after equilibrium is established, and from that he determines how much of the gas got adsorbed onto the surface. And he does this at varying pressures, and he finds at each pressure on top what is the amount of surface that is covered by the gas. And if you did this, as he has done this, and if you now plotted, take this data that he has given you, and if you plotted A, which is x over m, as a function of pressure, what you will find is that you will find something which looks like this. And you can take the data, take the slope, which is just the difference between two A's. So, if you take this old data that you have got, take the difference here over the difference here, and you will find that the slope here is high, which is in the initial portion, and as you move further and further out, the slope decreases, which gives you this kind of appearance. This is for argon on coconut charcoal at minus 78.3 degrees Celsius. Herbert Freundlich did a series of experiments where he changed this, the gas that is there, and also the solid that is used. And he found that no matter what gas he took and what surface he had, the general appearance of this graph was always sort of similar. They all had a similar sort of appearance, a sharp rise and then a tapering off as the pressure increased. This is what he finds, it is in general. So, this is in general for any gas and any solid. And he then tried to establish a relationship between the area covered, that is this A, and the pressure, and he found that x over m is related to the pressure through a relationship which looks like this. A, that is x over m, is equal to a constant times the pressure raised to 1 over n, where n is greater than 1. So, for different gases with different substances, K would be different and 1 over n would be different. So, in the case of argon, for example, what he finds is that A happens to be for argon at minus 78, A happens to be 3.688 times P to the 0.6. This is what Freundlich found. So, these constants here, this one and this one, are functions of the gas, the solid and the temperature. So, if you did this experiment with the same gas at a different temperature with the same substance, coconut charcoal, you will get a different A and a different 1 over n. And it turns out that if you did this not with a gas, but with a liquid. So, I take a solid surface, if I take a solid surface on top of which there is a liquid whose concentration is a liquid with concentration C, Freundlich found a very similar relationship, that x over m is k C to the 1 over n. And here is some representative data again. This is for the adsorption of acetone in water on blood charcoal. Well, let us not worry about what blood charcoal is. It sounds gruesome, but in any case, this is what he found. Here is the concentration and here is A for varying concentrations. And again you will find a similar sort of relationship. And if you plotted this, what we are saying is that it will have a very similar appearance to what you saw when you had a gas adsorbed from a solid. And this is data once again of Herbert Freundlich. And so it goes on. So, once again, whether it is a liquid on top of a solid, so I will just generalize, I will plot A, which is x over m, as a function of either P or C. And if you plotted this, what we are saying is both of them have an appearance which looks like this. And this is this appearance k and 1 over n depends on, very important, it depends on the adsorbate. I introduce adsorbate because that is something that is a term that you need to know. Adsorbate means the thing that gets adsorbed, the adsorbent, that is the solid which does the adsorption, and the temperature. So, it depends on these three factors. If any of them change, then k would change and so would 1 over n. And 1 over n, it turns out from practice and experiments that 1 over n has a smaller range when you have a liquid as opposed to a gas. But that is something that you need to know, but that is a general observation. But this general behavior is something that you need to know, that the amount of species that gets adsorbed from either a liquid or a gas which exists on top of a solid, that amount is related to the pressure or the concentration in the solution or the gas on top of the solid through this relationship x over m is equal to k C 1 over n. And you can then do some simple mathematical manipulation with this. You take the logarithm on both sides. So, you take logarithm of x over m, which is log a, which is equal to log k plus 1 over n log p or c, depending upon whether you have gas or liquid. So, if you made a plot of log x over m, if you plot log a versus log p or log c, I have taken in all these cases after we discussed the gas phase and the liquid phase separately. Now, I have generalized. So, I do not differentiate between whether I have something in the gas phase. If it is gas phase, I will write the pressure here. If I have the liquid phase, I will write the concentration. So, do not get confused by the symbol P by C. What I mean is that if I have gas, I will use log P or I will use log C. So, maybe I should just change this. I will say log P or log C, depending upon whether we have a gas or we have a liquid. And what we are saying is this plot looks like this. So, this has the form y is equal to c plus mx. So, that is the intercept and this is the slope. And this x, this is a mistake, I should not use x, call it x prime. So, x prime happens to be log p or log c. So, if I plotted y versus x prime, where x prime is log p or log c, I will have an intercept here which is log k, a positive slope. So, this is, if I it's horizontal, it is 0, positive slope, which means that it will go like that, and this slope is 1 over n. So, I could determine from that data that Freundlich has, which I have given to you. If you took that table and you plotted log x over m versus the log pressure, then you will get a curve like this, and this intercept and this slope will then determine what k is and 1 over n is. And this is a general observation. So, let us then try and do a little bit more experiments, then, because we have already said that the appearance looks general, but the specifics, that is how k behaves or what n 1 over n is, will depend upon the gas or the liquid on top of the surface and also the temperature. So, if I now measured the x over m as a function of temperature. So, I am plotting log A versus log P or log C as the case may be, and I am doing this for different temperatures. So, if I took one temperature, I would get something like this, call this T1. If I measured a different temperature, if I did this same measurement at a different temperature, call it T2, I will get something which looks like that. And if I did it at a third temperature, so call this T2 here, and if I did it at a third temperature, which I will draw in green, that will be T3 here. And can we now predict whether T1 is greater than T2 is greater than T3, or whether T1 is less than T2 is less than T3? So, the question before you is if this is the trend, what is the trend in the temperatures? Can we answer that question, and how do we answer the question? This is not hard to answer. All that you have to do is to appeal to Le Chatelier principle. You apply the Le Chatelier principle. Adsorption, we said, is a process in which there is some kind of bond formation between the adsorbate and the adsorbent. So, delta H adsorbent, delta H of adsorption is less than 0, which means that as you increase the temperature, what do you expect to see? You expect to see that this equilibrium will go down. So, this means that T1 is less than T2 is less than T3. That is, that as you increase the temperature, the amount of gas that gets adsorbed will decrease. And you can either argue on the base of Le Chatelier principle, because this heat of adsorption happens to be a negative quantity, and we know that if you have a negative quantity, if you increase the temperature, it will go in the reverse direction. The equilibrium gets shifted in the reverse direction, and that is what we see. The other way to argue about this is an interplay between delta H and delta S. So, when you increase the temperature, the solution or the gas which is on top of the solid, its motion is increased, and when its motion is increased, there is an extent of binding that happens from the gas to the solid that has a fixed energy. So you have to compensate between this thing that binds and this thing that is rattling around like this. And if this has more energy, this has more energy to kick things off which are already bound. So, the amount of stuff that gets adsorbed will decrease as the amount of motion on top of the solid increases, and the amount of motion on top of the solid is governed by the temperature from the kinetic theory of gases or liquids. So, there is a very simple explanation. As the temperature increases, the amount of adsorbed species goes down. So, quick recap, what have we done? We said that when you have an adsorption phenomenon happening, first of all, there is a simple relationship between the amount of adsorbed species and the pressure on top through this Freundlich relationship. And the second is that as you increase the temperature, the amount goes down. And each of these figures that you have, the red line, the blue line, the black line and the green line, each of these correspond to a fixed temperature. So, each of these is called an adsorption isotherm. So, you have what is called a Freundlich adsorption isotherm, and there are other isotherms attributed to other people. We have just touched a small portion of it. This is the Freundlich isotherm. There are other things which are more popular and more commonly used. There are some things called the Langmuir adsorption isotherm. There is another thing which is called the BET adsorption isotherm, but in any case, that is not something that we need to go into. But these two important things that you will need to keep track of. Okay, now we will try and understand a little bit about adsorption phenomena. We won't try to understand why the adsorption isotherm is the way it does look, but we will try and understand a little bit about what happens when you take something in the gas phase and when it approaches a surface. There are two things that happen, two kinds of adsorption phenomena that typically happen when you have a species in the gas phase on top of a solid. The first thing that happens is what is called Physisorption. And there is another thing which is called, obviously from this first name you know what the second thing is going to be, that is called Chemisorption. Surprise, surprise. One is Physisorption and the other is Chemisorption. So, imagine that I have a surface and all my surface are round spherical things and I have some gas phase molecules here, and for convenience let us now make this not single dots on top, we will make this double dots, which means that this is a diatomic molecule. Each of these things on top is a diatomic molecule. And what we are trying to do is, as the diatomic molecule approaches the surface, what is the kind of interaction that a diatomic molecule encounters as it approaches the surface. That is the kind of thing that we are trying to look at. And you are asking yourself, why a diatomic molecule? Why diatomic molecule? Because very often when you are doing catalysis, for example, as I am a chemist, if you are interested in the reaction of N2 plus 3H2 to give you 2NH3, each of these things is a diatomic molecule. So, very often as chemists who might be interested in catalysis, we are interested in how a diatomic attaches to the surface, because that has industrial importance. But whatever we discuss in terms of diatomics is also true of other things. And what we are going to do is to look at the potential energy as this diatomic molecule approaches the surface. So, we are going to look at potential energy as a function of distance from the surface. Okay. So, this is the lead in to the next what we are going to discuss. So, I am now going to plot the potential energy as this diatomic molecule approaches the surface. So, on the x axis then I have the distance r, call it. So, distance from the surface, and here I have the potential energy. Now, when the molecule, when the diatomic approaches the surface, what happens is, we already said that the surface has unbalanced forces, right. So, here is a surface and you take this molecule, for example, or atom or molecule or whatever, this is attracted or has forces on all this, on all these sides, but there are some unbalanced forces on this side, right. So, when this molecule approaches a surface from the top, what happens is, because of this unbalanced force on this atom, when it sees this, this blue surface atom is likely to pull this thing, and so its potential energy would drop. So, this potential energy drops, and when it drops, it gets, and this drop is arising as a result of the van der Waals forces, intermolecular forces between the gas phase molecule and the surface atom. So, the potential energy drops, it drops up to a point after which if I push the diatomic molecule closer and closer to the surface, its potential energy would start to rise. So, it goes down up to a point and then it starts to rise. The exact details of how this curve looks is not something that you and I have to worry about, but this is the general form. There is this dip, and this dip here, this distance corresponds to where this diatomic molecule has come and attached itself to the surface. That is the equilibrium distance of this diatomic molecule with the surface. That is where you have the minimum. Any time you push it on top even further, then the molecule, the energy increases. So, this is where I have a weak intermolecular interaction between the diatomic molecule and the surface, and the kind of force that we have got are simple van der Waals forces. So, this one here is weak van der Waals forces. It is the same force that leads to imperfections in real gases. The fact that all gases can be liquefied is a result of the intermolecular force that we have, and that is exactly the reason that we have this, except that here this intermolecular force is not between two gas particles, here it is between one gas molecule and the surface atom. And since it is a weak intermolecular force, this thing here, this delta H of adsorption is of the order of about 20 to 40 kilojoules per mole, typical of the kind of delta H of condensation. It is of the same order as what you would see when you have delta H of condensation or vaporization or something. When you go from liquid to gas or gas to liquid, that process, that is also something related to the weak intermolecular forces. So, you would imagine that this adsorption phenomenon here is similar to that. And this process here that happens, and this happens with all gases, all liquids on any kind of surface. So, it is absolutely not selective, and this is exactly what you have in Physisorption. This is a completely non-selective thing. Any gas you put, it will get adsorbed onto us, any surface that it sees. Yes, this depth would be different and this length would be different, but otherwise this is a general phenomenon. Now, what happens is, for some gases that are on top of some surfaces, you will find that after a while, if you push this even further, this diatomic molecule would then fall apart and will get adsorbed as two atoms on each of these surfaces. So, to give you a concrete example, imagine this was H2 and this was nickel surface. Initially, when I had this, this was nickel H2, and now I have nickel here. This is two nickel atoms on which is adsorbed a hydrogen atom. And so, what happens is, this potential energy for surface is only for the diatomic molecule. You plot a different diatomic surface and that looks like this. This corresponds to the dissociation of hydrogen into hydrogen atoms, and here this corresponds to the nickel hydrogen. So, that is, I have a hydrogen atom attached to a nickel surface, and this thing here is much bigger. I have now formed a chemical bond. So, this is delta H of adsorption in this case is of the order of 100 to 250 to 400 kilojoules per mole. Now, the exact numbers that you will see will vary upon the book that you look at, but the idea is, and that is the difference between what we have here and what we have here. The difference is this is much bigger. So, you have a larger well, and this larger well is because you have formed a chemical bond. So, here we have a chemical bond. So, in one case, so we have two things that we have learnt. We have one, a physisorption, which happens with all adsorbates, with all adsorbents. So, this is non-selective. It has a delta H of adsorption which is of the order of 10 to 40 kilojoules per mole, and it looks like condensation. It is completely reversible, which means that I can take this and I can heat it and the thing that is adsorbed will go away. What else did we see? And that if you looked at chemisorption, the things that we have looked at so far, it is selective, which means that if you had, instead of hydrogen, if you had some other thing, it might not adsorb onto nickel. So, it is selective, it does not happen with everything. It is irreversible sometimes, very often, and it has a delta H which is of the order of 100 to 250 kilojoules per mole. And I repeat that these numbers will vary depending upon which book you look at, not to worry, but the key is that there is a chemical bond formation. Here it is intermolecular force. Physisorption happens almost instantaneously, which means that you only have to stick it in and it will stick a gas into a solid, and almost instantaneously you will have some adsorption. This happens in finite time, and this one there would be no activation energy. Whereas here there is activated adsorption. What do I mean by that? Let us go back and look at that slide we had from previous. Here it is again. So, if you thought about it, hydrogen approaches as the diatomic molecule, it approaches the surface. So, this is the surface, right. So, this is 0, R equals 0 corresponds to the surface. So, the hydrogen molecule approaches from this side, and when it sees some distance it gets adsorbed, which means that the whole molecule goes and sticks to it. There is no rearrangement of the electron between the surface and the adsorbed molecule. No electronic rearrangement in this situation here. Then as you go further, you push this molecule, it has to go over an energy barrier. After it goes over this energy barrier, this diatomic molecule breaks up into two, and each of these atoms adsorbs onto the surface, and so now you have 2 hydrogen atoms. This here is the energy of activation to go from the physisorbed state to the chemisorbed state. Let us do this once again, because I think this figure has become a little bit too busy. I will redraw this and just illustrate what are the important points. So, we have energy on this axis, potential energy. We have distance from the surface on this axis, and we have one potential energy curve which looks like this, and another potential energy curve which is much deeper like that. Okay. This is the delta H of physisorption. This is the delta H of chemisorption, and this thing here is the energy of activation to go from the physisorbed state to the chemisorbed state. Okay? This is the energy of activation, which means that because there is an energy of activation, what you are going to see is that as you raise the temperature, the rates become much higher of chemisorption. This point here, if I am looking at, if this surface is what we have looked at is the R nickel to H2, then this point here corresponds to dissociated hydrogen. This corresponds to nickel H2. So, this here, this energy here corresponds to the dissociation energy of H2. And you can see what is happening. So, this is related to the condensation energy or the enthalpy of condensation of H2. This is bond formation here. So, this is going to be much deeper. So, this is chemisorption. So, not all molecules, that is in the gas phase, can form bonds with things that are on the surface, which is why this thing becomes selective. Not always are we going to have a bond between the adsorbent and the adsorbate. Only appropriate cases you will have. So, this is a very selective thing. This one is anything can adsorb to anything else. So, this is non-selective, and it is also reversible because this depth is very small. So, if I heat it, whatever is adsorbed, I provide it enough energy, it will run off, it will go off into the gas phase. Whereas here, because there is bond formation, I can still break it, but the amount of energy required to break it is much higher. And realize what has happened. If you take hydrogen for example, dihydrogen for example, the bond energy of dihydrogen is very, very high. And if you took this dissociation of H2 to give you 2H, this bond dissociation energy is very high. And effectively in this case what you have achieved is that by just this activation barrier here, you have been able to take H2 from here and make it NiH, right, because here what you have is this point here corresponds to Ni with a hydrogen attached to it. So, effectively with much lesser energy you have been able to break dihydrogen and convert it into 2 hydrogen atoms. This is a very, very important thing, and this is how catalysts work. When you have the Haber-Bosch process where I have ammonia react with hydrogen, and I have a catalyst, I have to break, and it has been known that the way this reaction happens is nitrogen breaks to give nitrogen atoms, hydrogen breaks to give hydrogen atoms, and then I have a reaction between the two atomic species. So, if I have to have a reaction between nitrogen and hydrogen, if the energy required to break each of these species is very high, then the reaction is going to be very slow, and that is where the catalyst surface becomes critical, and this is the key to explaining this. What we have done here, we have shown now that if you took a diatomic species and you brought it near an appropriate surface, you could find a situation where the energy required to break the diatomic molecule and to get two separated atoms is much lesser than what you would need if you were to break this in the gas phase. So, H2 gas going to H gas, delta H is very high, whereas H2 gas going to surface attached hydrogen in the solid state, this delta H is very small, and that is how catalysts work. So, what we have now discussed today is that we have looked at chemisorption, physisorption, adsorption isotherms, and it is important. So, the 3 or 4 essential things that we learned is that when you have a surface on top of which you have some species, the species will get adsorbed, and there is a relationship that exists between the amount of adsorbed species per unit mass of the solid and the concentration or the pressure that exists in the above phase. So, that is the adsorption isotherm, and we said that the adsorption isotherm, as temperature increases, the amount that is adsorbed decreases. We also discussed physisorption and the differences between physisorption and chemisorption, and we showed with a potential energy diagram what is the difference between physisorption and chemisorption. Okay. In the next class, we will now discuss what catalysis is. So, what we have learnt here, the amount of adsorption and also differences between physisorption and chemisorption will always be in the back of our minds when we are discussing catalysis. So, when you look at the Haber-Bosch process, for example, a very popular example with me is N2 plus 3H2. So, you need a reaction, and if you need a reaction, you need to have it adsorb a catalyst which adsorbs nitrogen and hydrogen. And so, these are things that we will come back to again. With that, we will close for the day.